Hello, and welcome to this series of videos on randomized algorithms. My name is Mary. Before we get started, I should say that these videos are largely based on the excellent lecture notes by Greg Valiant. I have included a link in the description below to where you can find those lecture notes, or some version of them, along with some exercises that sort of go along with these videos. So let's get started with the basics. What is a randomized algorithm? Formally, we should have a computational model, but we're not going to worry about the details too much in these videos. If you've taken some complexity theory, you may have seen a model like a Turing machine or a random access machine for modeling computation that maybe looked something like this. So you've got some box, which I'll call a Turing machine or random access machine or something like that, and it has access to some tapes. In particular, it has access to some tape with the input written on it, and access to some scratch tape for its memory. And we imagine that maybe it has read-only access to the input, so there's some read-only head that points to the input, and it has read-write access to its memory, so it has some other head pointing to the memory tape. And it can move these heads back and forth, and it can read or write as appropriate, and at the end of the day it's supposed to do some computation based on the input. So that's what a computational model might look like. As written here, this is a deterministic computational model. There's no randomness. So when we take a computational model like this, and we change it to a computational model for a randomized algorithm, all we're going to do is we're going to give this thing access to some random bits. That is, we're going to give it access to some tape that looks like this, that has a bunch of independent, uniformly random bits on it. Technically, I guess this tape should be infinite. There we go. And again, this machine is going to have maybe some read-only head that points into that. Okay, so for the purposes of these videos, this is about as much detail we're going to go into about our computational model. A simpler way to think about it is that whatever computational model you have in your head for a deterministic algorithm, keep that computational model and say that your deterministic algorithm is now allowed to flip some random coins. Let's make a few observations about this computational model. The first observation is that the output of a randomized algorithm is a random variable. The second observation is that the execution path of a randomized algorithm is also a random variable. That is, let's think of the input to our algorithm x as fixed. And then our algorithm is going to flip some coins and do some stuff. Here, h and t are going to stand for heads and tails. We can write the stuff that the algorithm does as some function, alg of the input x, and also the random coins that it flips. Notice that with this way of looking at it, we can imagine that the algorithm flips all of the coins up front, or it can flip them kind of as it goes along. Formally, it doesn't really matter. All we're interested in is this function of the input and our random coins. After our algorithm flips its coins and does some stuff, it's going to output an answer. And formally, that's going to be the output of this function. So what these observations are saying is that both the output of this function and the stuff that it does are random variables, meaning that they are functions of these ri's, and those things are random. What these observations mean is that the following statements are reasonable statements to make, meaning that they parse and they make mathematical sense. The first is that for all inputs x, the probability that the algorithm is correct on x, that is, the probability over r1, r2, ... that alg of x, r1, r2, ... is correct, is greater than or equal to something. Right, that this is a reasonable statement that we could make, and in many cases, perhaps it is a desirable statement for us to make. Another reasonable statement for us to make is that for all inputs x, the variance of the running time of the algorithm is not too large. So once again, this running time is a random variable because it depends on these ri's, and so it makes sense to talk about its variance, and it made sense to say that that should be small for all inputs x. So these are, of course, not the only reasonable statements that we could make about a randomized algorithm. I just want to give you some examples of the sorts of statements that make sense to make and that we might be making. In these videos, we're going to consider two types of algorithms: Las Vegas algorithms and Monte Carlo algorithms. So Las Vegas algorithms always output the correct answer, but they might be slow. So in this case, the output is deterministic. It's always the right answer. But the running time is a random variable. And typically, we're going to demand that the expectation of the running time is finite. An example of a Las Vegas algorithm that you might have seen before is quicksort. So quicksort is always correct. It always outputs a sorted list. And usually it's fast, but in some very bad cases, if it gets unlucky, it might be slow. In contrast, Monte Carlo algorithms are algorithms that are always fast, but they might be wrong. So in this case, the output is a random variable. It might be right or wrong. But the running time is deterministic, or at least is bounded by something deterministic. An example of a Monte Carlo algorithm that you might have seen before is Karger's algorithm for minimum cuts. And if you haven't seen Karger's algorithm before, we'll probably see it in a future video. When we're talking about randomized algorithms that might be wrong, that is, Monte Carlo algorithms, if those algorithms just output a yes or no answer, it makes sense to talk about one-sided error versus two-sided error. So with one-sided error, what this guarantee means is that if the correct answer is yes, then the algorithm will say yes with probability 1. So it's always right if the answer is yes. On the other hand, if the answer is no, then the algorithm will say no with at least some positive probability, with some epsilon greater than 0. Now, this might seem like a pretty weak guarantee. If the answer is no, don't I want to be right with like high probability, like 90%, 99%, probability 0.9999999 or something like that? It turns out that actually this guarantee is just as strong as that. So here's a fun exercise. Take this guarantee and turn it into a guarantee that the algorithm is correct, say, 99% of the time. If you don't see it already, why don't you pause the video right now and think about it. Okay, so you might have figured out that the solution is to just repeat the algorithm a bunch of times. That is, let's say we have an algorithm that satisfies this guarantee with some teeny epsilon greater than 0, and let's just run that algorithm a bunch of times. So for I equals 1 up to t, we're going to run the one-sided algorithm. If it says no, then we know that with probability 1 the correct answer is no, so we'll return no. And if we do this all t times and we never see a no, we'll say, okay, well, I guess the answer is yes, and we'll return yes. So I claim that if t is large enough, this will actually have a very high success probability, or very low failure probability. So let's work that out. So as we said before, if the correct answer is yes, then we'll definitely return yes, because the algorithm will never say no. But if the correct answer is no, then the probability that we accidentally return yes is small. More precisely, the probability that we accidentally say yes is the probability that this one-sided algorithm fails in all t trials. That is at most 1 minus epsilon to the t, because the probability that it fails once is maybe not so small, 1 minus epsilon, but the probability that it fails t times independently is that raised to the t. And this is quite small. So here comes a very, very useful approximation. 1 minus epsilon is always less than or equal to e to the negative epsilon. Super useful approximation. Let's use it here. This is less than or equal to e to the minus epsilon t. So this means that if we choose t large enough, perhaps to the tune of like 10 over epsilon, then this number is super small. It's like e to the minus 10, which is tiny. Okay, so that's how we can boost an error guarantee that looks like this into one that is successful 99% of the time in a no instance. So that explains why this is a meaningful guarantee to have. All right, so that was one-sided error. We can also talk about two-sided error. So for an algorithm with two-sided error, the guarantee is that no matter what the answer is, whether or not the answer is yes or no, the algorithm is going to be correct with probability at least 1/2 plus epsilon for some epsilon strictly greater than 0. So again, this might seem like not very good. If epsilon is equal to 0, then I can always get an algorithm that's correct with probability 1/2 just by guessing randomly. Right? And this is just a smidge better than that. But just as was the case with one-sided error, with two-sided error, we can amplify our success probability by repeating it a bunch of times. That is, we can ask the same question: how can you amplify an algorithm with this guarantee into something that's correct 99% of the time? And we're going to have the same answer. That is, we're going to repeat it a bunch of times. So in this case, the algorithm is going to look like this. for I equals 1 to t for some parameter t that we'll choose in a moment. Let's run that two-sided algorithm and just take majority vote. If it says yes more than half the time, output yes. If it says no more than half the time, output no. So I claim that this also successfully boosts the success probability to something really big. More precisely, I claim that the probability that this majority vote is incorrect is at most e to the minus 2t epsilon squared. So I'm not going to prove this claim right now. The proof is a bit of a tedious computation. You can see it in the lecture notes if you're curious. But we'll actually see some less tedious ways to arrive at this same result later, so let's hold off until that. However, given the claim, notice that if t is sufficiently large, to the tune of, say, 20 over epsilon squared, then again, the probability that this algorithm, this sort of repeated algorithm, fails is very small, less than or equal to e to the minus 10. Also known as tiny. Okay, so hopefully that explains why these guarantees, one-sided error and two-sided error, are reasonable guarantees to have, even though at first sight they might seem a little bit weak. Okay, so that's it for this video. Hopefully now you have some idea of what we mean by a randomized algorithm, and in the subsequent videos, we'll see a bunch of different examples of randomized algorithms, and we'll also see a bunch of different examples of tools for analyzing them.